Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at Akgec Engineering College, Ghaziabad. I am before you to present the video lecture for the complex topic series. So here I am presenting the video lecture for the subject digital signal processing, whose code which code is as per the AKTU curriculum, that is BEC 503. So from the first unit, which is dedicated to the realizations of IIR or FIR filters. So in this series, I have chosen the topic the realization of IIR system. So in this lecture, I will give the brief review or regarding the how can we realize the IIR system. That means when we are going to design any hardware for any IIR system, so what is the requirement of the hardware component, like how much adders, multipliers will be used there, memory elements, how much memory elements will be implemented while designing the IIR system. So for that point of view, just I have started with the topic realization of IIR system. So when we are realizing any IIR filter, IIR is nothing but the infinite impulse response filter. So infinite impulse response system. So for that particular system, the causal IIR system are characterized by the constant coefficient difference equation for an LTI system, which is given by y of n is equals to summation of k is equals to 1 to capital N ak y of n minus k plus summation k is equals to 0 to m bk x of n minus k. So this equation 1 corresponding to the differential equation for an LTI system, where these constant ak and bk, these are the ak and bk are the constant with condition that a naught is not equal to 0 and the m is much less than equals to capital N. So while keeping these conditions in the mind, we have designed considering the equation first for the causal IIR filter. So after that, we are considering this equation. Now take the Z transform of equation 1, which is given by the equation yn. Yn is nothing but the just a minute. Yn is the time domain and the yz is the z transform of the function yn, which is assigned given by y z is equals to summation of n is equals to minus infinite to plus infinite yn into z raised to power minus n. So with the help of this formula, we can find out the z transform of any function with the help of this, like yz is equals to summation n is equals to minus infinite to infinite yn z raised to power of yn y z raised to power of minus n. So when we put this equation in the place of yn, so the final conclusion result which is comes out is equals to yz upon xz, which is equals to the impulse response of the transfer function of the overall system h of z is equals to yz upon xz, which is given by summation of k is equals to 0 to m bk z raised to power of minus k upon 1 minus summation of k is equals to 1 to n ak z raised to power of minus of k. So that is the overall transfer function for any of an IIR system, which is in the z domain is explained by this function hz is equals to summation of k is equals to 0 to m bk z raised to power minus k divided by 1 minus summation of k is equals to 1 to n ak z raised to power minus of k. So with the help of this transfer function, we can realize any IIR filter, where these BK are the feed forward path coefficient of the numerator, and KK is the forward path multiplier, forward path denominator coefficient here. So while keeping all these in mind, we can able to design the any IIR, sorry, realize the any IIR filter. So what are the methods? So now the next point, that is the how can we design with the help of technique, which with the help of that technique we can design any IIR filter realization. So for that point of view, the four categories are characterized. The first one is direct form realization, second is cascade realization, the third one is parallel realization, the last one is the ladder realization. So these are the basic four categories. With the help of these four methods, we can design, we can realize any IIR filter, where the most popular, that is the direct form realization. The direct form realization is further classified in the two categories, that is the direct form 1 realization and the direct form 2 realization. With the help of these two methods, further direct form is categorized into two categories, direct form 1 and direct form 2. So in the direct form 1 realization, as we can see that in the previous equation, that Hz is equals to this one equation, let's say this is equation number 2, we have assigned this. So with the help of these second equation, we can see that the upper numerator part just denote the zeros of that system, and the lower part, the denominator part, which will represent the poles of the system. So on the basis of the arrangement of these poles and zeros, we can realize the any IIR filter in the direct form method. So in the direct form 1 method, where the first we have to realize the zeros, after that realization of poles. That means poles, zeros are followed by the poles to realize any IIR system. In the direct form 2, the just process will be reversed. The first we have to design the poles, then after that we can realize the zeros. So the complexity can be reduced, hardware complexity will be reduced in these two methods. How can it will be reduced, we will discuss later on. So these are methods we have discussed. Now we will focus on to the first one, that is the direct form 1 realization. So the direct form 1 realization, in this process the filter can be realized with the help of the Hz, let's say overall transfer function, which can be assigned as broken into the two function H1z or H2z, okay, where we have given the input xz or xn, intermediate term we have included wn, its z transform is wz, then we have to get the output yz or yn, where this will be the complete h of z, which h1z and h2z, where the h1z is the zeros of the system and h2z is the poles of the system. So that means when we are designing any realizing any IIR filter with the help of direct one, so first of all we have to design the first poles, sorry, zeros. After that, we can design the poles. So, in this realization, the equation 1 which we have discussed in the previous one, we can write it like that: y of n is equals to summation of k is equals to 1 to n ak of y of n minus k plus w of n, where the w, this wz or wn is equals to, we can write it like that: wz is equals to xz into summation of k is equals to 0 to m bk z raised to power of minus k. So, in this process we can now design it, that corresponding, if we write the wn which is equals to summation of k is equals to 0 to m bk of x of n minus k. So, in this we can now design the overall yz. If we can now write it like this, yz is equals to of wz upon 1 minus of summation of k is equals to 1 to n ak z raised to power of minus k. Now, with the help of this dividation, when with this methodology or the derivation, we can now design. So, at the realization time, when we will realizing it, so first of all we have to realize the zeros. Zeros means what? This wz part, that is the wn k is equals to wz is equals to xz, which is multiplying with the factor k is equals to 0, 1, 2 and bk z raised to power minus of k. Now, first we have to derive the realize this function. So, when realizing that, the realization will become like this: the input we are giving here, that is the x of z or x of n. X of z multiplied the summation of k is equals to 0 to that is m bk z raised to power minus of k. So, when we are summation k is equals to 0, 1, 0 to power m bk, so when we put the value of k equals to 0, first one, so it will become b naught plus b1 z inverse plus b2 z inverse up to this till the b m z raised to power minus of m, like this. So, we have to now just first of all realize this part. So, while realizing this part, the first of all xn will followed with the coefficient b naught, where we are getting the output wn. With the help of this, we are so after b naught, then what? Z inverse followed with b1, and it is going to add. It is going to add here. Let's say just and we are, let's say, get the output here wz. Then after that b1 b naught, here the output we are getting what? B naught xz into b naught plus b1 z inverse. Then if we can see in this sorry, z raised to power minus 2, z raised to power minus 3, like this. So, we can now b1 z raised to b1, this one we can get here. Sorry, the mistake, something, sorry, we can now, it will be like this, b2 b1. So, the output we can first check for these two, the b naught plus b1 z inverse. Now the next one b2 z raised to power minus 2. then z raised to power minus 2 will z raised to this one and this one multiply. We are getting the output here what? Z raised to power minus 2 with the multiplying with the coefficient b2, and it is going to add here and add off this one. So in this way we can now design this. So it will be continue up till the next point, that b of n minus 1, and the last one that we will get, that is z inverse up to this is of now b of capital N. So in this way, that is here this is x n minus 1, x of n minus 2, x of n minus n plus 1 like this, and last one here x of n minus capital N we will get. So this part is respective to the zeros. After that, what we are doing, the next part we have to derive, that is the pole knot. Pole is what? This one 1 minus of this one something. So what we can here, the 1 plus summation a1 z raised to power minus 1 plus a2 z raised to power minus 2, like this we can now derive it. So this one part, that is what? Wz. Okay. So this Wz is now going to add here like this one. First coefficient is 1, which you can see here, this part, this one part you can see 1 we have to design. So the 1, after that this part minus of this something plus or minus a1 z raised to power minus 1. So we can now derive here z inverse a1, it is going to add here, then a2 z raised to power minus 2, then it will become z raised to power minus here we will get z raised to power minus 2 with multiplying with the multiplier a2 and so on. This you can now, we will continue it. Then last, it is now z inverse. It is now going to add, and we will get the output here what? Yz or Yn. So this now, this part which has been designed here, that is the corresponding poles of the system. So now the overall we have to realize it in the 2 stages. The first one we have realized the zeros, then we have to realize the poles. Now finally for the complete, this means the direct form. Now we will now add on all these. So this will complete the structure you are looking here, that is the regarding corresponding to the direct form realization of any IIR filter with the direct form 1 method. In the direct form 2 realization, when will we go? So in the direct form 2 realization will follow the where we have divided the overall Hz into the 2 parts, like this one. This one is the overall H of z. We are getting the output Yz or Yn when we are applying the input Xz or X of n. So in this method, the position will be reversed of these 2 transfer functions, that where in the first one we have realized the zeros of the system, then poles. But in this direct form 2 realization, the first poles will be realized, then zeros will be realize. So, in this category, if we will see, the H1 Z is corresponding to the 1 upon 1 minus summation of k is equals to 1 to n a k z raised to power of minus k, and H2 of z is equals to summation of k is equals to 0 to m b k z raised to power of minus k here. So, now we can realize the system here. Similarly, similar passage for the equation 1, that is wz is equals to x of z upon 1 minus summation of k is equals to 0 to m a k z raised to power minus k, and yz is equals to what? Wz into summation of k is equals to 0, it is from k is equals to 1, k is equals to 0 to n bk z raised to power of minus k. So, in this process we will now realize the direct form 2 realization. So, in the direct form 2 realization, when we will designing, so the first of all we have to derive what the poles. So, poles means this one 1 minus something k is equals to 0 1 to m a k z raised to power minus k. So, in this process now xn we are realizing here the z inverse, this one part is 1, then a1, then a2 z raised to power minus 2, it will become z raised to power minus 2, like this, and so on. It will continue. N minus 1 z inverse, then multiplier a n, we will apply this. So, this part now corresponding to your poles. After that we have to realize the zeros, that is summation k is equals to 0 to m m a k b k z raised to power minus, then means b naught plus b1 z inverse like the previous one. So, when we will design it z inverse, so first of all this is b naught, then here we let us say the summation point wz which is common out here, then b1, then b2 z raised to power minus 2 it is now, then in the same way up to p of n minus 1, this one, then in the last that is bn z raised to power of minus 1. Now, we can get the output here yz or yn. So, this will part now include the realization of the zeros. So, this will complete structure will represent the realization of any IIR filter with the help of direct form 2 method. So, in this process when we will compare this result, this realization diagram with the help of the previous one, if we see the direct form 1, that you can see here the adder and multipliers will remain same between these two when we will see these two diagram in comparative way, but the major change is multipliers and the adders will remain same, not going to change. The same quantity what we are going to use in direct form 1, it will remain same into the direct form 2, but the major change will comes out here. The memory elements are using in this way z inverse for the separately we are calculating designing for the poles zeros part, then for poles part, but in this direct form 2, we have used only the requirement of the memory element or the Z inverse will become half. So, in this way the hardware complexity will reduce. So, in this way the direct form 2 realization is an effective method for the realization of any IIR filter with comparison to the direct form 1 method. So, this is now from my side for this basic realizations of any IIR filter with the help of direct form method. This is the book references I have taken here, that is the Salivanan. Thank you and Jai Hind.